Okay, welcome to this video in the series on the binomial expansion. This is the third one where we're going to look at a more advanced form of the binomial expansion that we do at A level. Now, this has advantages because it doesn't require n to be a positive whole number. N can be an integer that's negative, or it can be a fraction. Okay, so let's see how it works, and to do that we'll start with an example of 1 plus x to the power 5. Okay, so this is how I'm going to introduce this to you. So if we start with the expansion of 1 plus x to the power 5 using the method that you've already learnt about previously, which is this thing up here. Okay, so basically A is 1, B is x, and n is 5. So that's going to give us 1 to the power of 5, okay, plus, and then it's going to be 5c1, which is 5, then it's going to be 1 to the power 4 times 1 to the power 4 times x to the power of 1, plus then it's going to be 5c2, which is 10, 1 cubed times x squared, and then it's going to be 5c3, which is also 10, 1 squared x cubed. Then we're going to have 5c4, which is 5, times 1 times x to the power 4, and finally we're going to have x to the power 5. Okay, and if we tidy that up and take out all the unnecessary ones and powers of 1 and the brackets, we've just got 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the 4, and finally x to the power 5. So that's the simplified expansion of 1 plus x to the 5 using what we've already learnt. So how does that relate to what's going on here in this newer and more useful version? Well, let's take a few of those terms and see where they actually come from. Let's start with the 5 here. So the 5x, so in the term 5x, okay, the 5 actually comes from 5c1, okay, 5c1, which is the number of ways of arranging one thing within 5, if you like. And that is in turn from 5 factorial divided by 1 factorial times 5 minus 1 factorial, which is 4 factorial. Okay, and you can see that here. Okay, and now I'm going to write that in full and see what's actually going on. So we've got 1 times 2 times 3 times 4 times 5, and all of that is divided by 1 factorial times 4 factorial, which is 1 times 2 times 3 times 4. Okay, so that is that factorial fraction there written in full. And then I'm going to do some cancelling, and I'm going to cancel as follows. So I'm going to take out of there, if I just use a different colour for that, I'm going to take out there the 1 times 2 times 3 times 4, and the same from the bottom like that. And that's going to leave me with 5 on the top, okay, and on the bottom it's going to leave me with 1, or 1 factorial, which is what it actually came from. Okay, now we'll just look at the next term and maybe the one after that and see where this is all leading to. So I'm now going back to my expression, and I'm now saying that in the next term, which is the 10x squared term, the 10 has actually come from 5c2, and 5c2 has come from 5 factorial divided by 2 factorial, 3 factorial. So that is what it's come from. So we're talking about this term here, okay? And that is equal to 1 times 2 times 3 times 4 times 5. And that's being divided by 1 times 2, which is the 2 factorial, and 1 times 2 times 3, which is the 3 factorial. Okay, now if I cancel that out in the same sort of way that I did with the previous fraction, I'm going to take the 1, 2 and 3 out of there and cancel it with the 1, 2 and 3 out of there. And that's going to leave me with, okay, 5 times 4, and I'm deliberately writing them that way round. Okay, you'll see why in a bit. And that's over 2 factorial. Okay. Now I'm just going to do the next one as well. Now that's also 10, but you see that 10 has come from the not 5c2 but 5c3. Okay, so in 10x cubed, right, the 10 has come from 5c3. Sorry, I don't need a fraction line in there. 5c3. Okay, and 5c3 is 5 factorial over 3 factorial, 2 factorial. Now obviously it's got the same value as the one above, but the way I'm going to cancel it is different, and you should see why shortly. So if I write it in full, I'm going to write 1 times 2 times 3 times 4 times 5. Underneath, I'm going to have 1 times 2 times 3, and that's going to be timesed by 1 times 2. Okay, and when I come to do my cancelling now, I'm taking the 1 and 2 out there with the 1 and 2 over here. Okay, let me put the fraction line in as well. So I'm left with now, you see, 5 times 4 times 3 on the top and 3 factorial underneath. Okay, and in general, you see, this is what you've got to notice here. I've got these numbers descending: 5 times 4, 5 times 4 times 3. Okay, and that matches up with what's going on in here. Okay, so if I were to write out the expansion of 1 plus x to the 5, but using this format here, this is what I would be saying to myself as I did it. So I would be writing this. I'd be writing 1 plus x to the power 5, okay, equals, 1 plus nx, which is 5x, plus n minus 1, 5 minus 1, x squared over 2 factorial. So the factorial matches the power of x that I've just written down. Okay, my next term would be 5, which is n times n minus 1 times n minus 2 over x cubed there over 3 factorial. Okay, and the next term, I'll just quickly move through this, would be 5 times 4 times 3 times 2 times x to the power 4 over 4 factorial. And there would be one more term in this case, but it's very important that you see why it would terminate after this, okay? Because not all of these series will terminate. Some will go on forever, and that will happen when n is no longer an integer, okay? But in this case, n is an integer, so I'm following the same pattern. I'm getting my x to the 5 now, which is my last term, and I'm dividing by 5 factorial, okay? And if I were to try to carry on, what would happen? I would get 5 times 4 times 3, because this will work, but you'll see hopefully what will happen to the value of this now, times 2 times 1 times 0, x to the 6 over 6 factorial. And you could carry on, but there would be little point, because every term, including the one I've just written down, would be 0, okay? Because you're always going to have this 0 in here, which is going to cause the whole thing to be 0. So you can just cross that out, stop there, because this terminates, and it terminates at the x to the 5 term. And if you simplified each of those expressions above, you would have 1 plus 5x. The next term would be 20 over 2 factorial, which is 10, which will give us our 10x squared. Okay, we already know the result, but this is just showing it coming from a different way. 5 times 4 times 3 is, well, that's 20 times 3 is 60. 60 over 3 factorial is 60 over 6, which is 10. So it's 10x cubed. This comes to 5, because it's, well, 5 times 4 times 3 times 2 is going to be 120. 4 factorial is 24. That gives you 120 over 24, which is 5x to the 4. And finally, you've got here 5 factorial. That's 5 factorial, so you've just got x to the 5. So you can see it working there. And as I said, any term after this would be 0. Now, you should already be thinking ahead and asking yourself, well, suppose n wasn't an integer. If if n was a half, for example, this would never get to 0, because you would have a half, negative a half, negative 1.5, and so on. And it would never terminate. This series would be infinite. And that can be incredibly useful if x is very small, because as you raise it to larger and larger powers, it gets even smaller. So you get converging series that give you approximations to certain values. We'll look at some examples of that in the next video, but this is an introduction to the better version of the binomial expansion and how it can be used. Okay.